Hello and welcome to the new video, and in this video we will look at the ridge regression. So ridge regression is another form of linear regression which helps us improve the normal linear equation in case if there is a new unseen data which model has not seen and you want to improve the results based on the new data that you are seeing. So in this video we will see the explanation and Python implementation. So first of all, what is ridge regression? So just now I've given you a small definition that ridge regression is a regularization techniques which helps us basically improve the model for linear regression model to perform well in scenarios where there is a high variance as compared to the data which is used to train the model. So what that means is, so there is this data points which you have used when you have created the model. But when you put your model into a scenario where it has not seen the data points, now these data points can be of high variance, that means away from the line, and in that case normal linear regression may not give us a good output. So what ridge regression basically does, it uses regularization technique which basically penalize the model for this high variance and then creates a new line or a new structure on the fly and gives you the better output by reducing the variance. And we will see in a couple of minutes how it does that step by step. Alright, so just a quick definition of regularization. So it is a technique to penalize the model for the overfitting of data and adding a parameter which tune the model for better outcome. Like I said when I was here, that it creates or it penalizes the model by adding a bias and then it reduces the variance from the new data points. Alright, let's see it in the action. So example of linear regression, you must have seen my previous videos where I've explained about the linear regression, and here is a simple linear regression equation which is sales equals to 1 is basically the intercept plus 0.5 which is a slope multiplied with marketing. So then what we are doing is we are suppose adding the marketing value which is 10 to the slope, and the sales is coming as 6, maybe the $6,000. If we are adding another $10,000 model, 10,000 to the marketing, the sale will be increased by the $6,000. So things like this we will be explaining, we basically explain with the help of this model. Or the linear regression model basically helps us achieve these simple outputs, and that's what I have explained it over here with the help of the linear line, with the help of the chart. So over here just assume it is sales and this is marketing. The more you are spending into the marketing, the sales is going up, right? And that's what it has been shown with the help of a positive linear trend with a positive slope, right? So but if we are giving a bit of a twist to this by adding one more chart to it over here, as you can see, this is our original line, but let's say if there are new data points which have been added like this and this, in scenarios like this, when you will test your model, which is this, will not give the accurate output, right? Because this line is not the best representation of these data points, and these data points it has not seen. And this particular scenario is called the overfitting, where you have trained the model. For example, the outcome of this model is basically this equation. So basically you have trained the model so much that when you will expose it to the unseen data points like this or this, it will not give you the accurate output. So what you may need to do is retrain the model based on the new values, and probably you will get a second line like this, which is not a standard fit like this, but a line like this. And that's what ridge regression basically helps us. So it creates a bias like from this equation to this equation by penalizing the model. And with this little bit of bias, what it does is it helps reduce the variance between the actual and the actual and the residual. So for example, your actual value is this and your predicted value is this, and the difference between this is residual. So it basically reduces the residual between these two values, or the variance. So if you can see, the variance between this line and this data point will be higher than this line and this data point. And when you have the reduced variance, you will get the better output, which you can consume for further action. And that's what I have explained over here. Here we introduce a small amount of bias to not overfit the training data. So that means by adding more little bit of bias, we have moved from here to here. And this bias then resulting in reducing the variance in the unseen data. So variance between this line and this line is, this data point is reduced, and this then overcome the problem of overfitting as well. So this you can even explain in the interview, that if somebody is asking how you reduce the problem of overfitting, so you can take this example and basically help them with the, either if they have given you pen and paper, just simply put these data points over there and you will be able to explain it. Now let's see it in action by putting values. First of all, seeing the equation of the ridge regression. So ridge regression equation is basically sum of squared residual. That means the x minus x bar, the mean value. So what it has is basically, this is the x and this is the x bar, and then you are taking a square of it, and then you add the alpha. Alpha is basically the penalization, the how much the bias. So bias is basically from, so 0 is like absolutely no bias, and then you can have a value of 1, you can have a value of 2, 3, based on where how much you want to bias, and accordingly the slope is basically a penalization, that, or the the punishment to the model that it is deviating. Then this basically add a penalization to the model. So just to see how this entire thing basically works, so over here, penalty to the equation and how severe the penalty is, and this basically indicates the graph that we have seen in the previous slide, where this is our standard equation, but let's say after adding a penalization of 1, the line has moved from here to here, and now it is a new line like this, which is reducing the variance of the unseen data points. So if we see the new equation, so first of all, sum of squared of residual in case of a standard line chart will be 0, because all of the data points are coming over the line, and that's why this is 0. So sum of squared residual is 0 plus 1 multiply with slope square. So slope square is basically 0.5. If you remember from the previous equation, that sales equals to 1 plus 0.5 of marketing. If I remember it correctly, that's what the equation was. And 0.5 square is what we need to take as per the regression equation, because that's a slope square and we had the slope of 0.5. So 0.5 multiply with 0.5 multiply with 1 is basically your 0.25. That means when you have the data points actually on the line, but when you have the new data points, and based on the new data points for them, if we are adding the bias, then and the new slope when it comes, then what happens? So let's say we have moved to this line, and the difference between the actual data point and this line is basically 0.2. Then we'll take a square, because we need to take a square as per this addition of alpha. Alpha is, let's say, 0.1 in this case. You can have like from 1 to 2 to 3, or 0.1 also you can have it, but this is like just for the representation over here. You can have even 1 as well. So 0.1 multiply with 2 plus slope square 1 multiply with 0.3 square. So if you do the math, you will get 0.04 plus 0.01 plus 0.09 equals to 0.13. So in case of new data points, when we get the new slope and we added the sum of squared residuals into the equation, we get the new error rate, which is like 0.13. So in case of the normal standard line, the sum of squared residual plus the penalty was 0.25, but in case once you have applied the ridge regression and you have applied the bias, the penalty has reduced to 0.13, and that way when you apply the ridge regression you will see the better outcome as compared to your linear regression technique, especially in cases where there is the new data points represents the high variance. So let's see it in action within the Python and see how we can implement it. Alright, so here we are within the Python, and I have imported couple of libraries, standard libraries like pandas, spd, sklearn.linear model, and from that I have imported the rich, which is a rich regression. From sklearn.matrix I have imported the mean squared error just to calculate the error rate, and to reduce the squared effect I have taken the numpy array np, from which we will be using the sqrt, which is a square root method that reduces or that removes the impact of square. So first of all, what we have is the simple Boston data set from an understanding perspective, and we will say pd.read_csv, and since I have the database within the same location where this particular file is, I get basically the data set. So what I have not done is I have not executed this, since I have just written it but not executed it, and if I execute that I will get the file dataset. So if I just have couple of source data points, and if I increase the font for you, my apologies that I could not do it earlier, but I hope this is readable. So Boston pd.read_csv boston.hat gives you these observations, which has the crime rate, which has the nitrogen oxide, rooms, average age of the property, and based on all of these variables at the end you have the mean price of the property, like $24,000, $21,000, so on and so forth. So what we will going to do is we will going to produce a model on this using the rich regression technique. So for that, let's go ahead and convert this into an array, because as per any machine learning algorithm, they take the array values into the consideration, so or for the processing or for the fitting of model. So what we need is first of all converting this into an array. So what I'll do is Boston_array equals to simply Boston dot what method I need to use. So this could be an interview question. I have explained it in my previous videos as well, so remember that. Boston dot values. So now if you see the type of Boston_array, it is an array, and if you see the type of Boston, it is the data frame. So we have converted the data frame into an array, which we can then further process. So remember that it can come in an interview. And after that, what we need is basically an x. So x is Boston array. We will take all the variables, first of all the rows, comma, from 0 to 13, and for y, so you have total 14 variable, and as you know, the last point is exclusive, and that's why we have taken the 13 colon and 13, which is the last variable. When you apply this 0 to 13, the last number 0, the 13 is exclusive, and you will get the value from 0 to 12 in that case. Alright, so let's go ahead and execute it. And now just to confirm, see the values of y, 24, 21.6, 34.7. So if you go over here, 24, 21.6, 34.7, 33.4, 36.2, perfectly fine, right? After that, what we can do is we initialize the rich regression. So lin IDGE, since it is from the linear family, I can have lin rich or lin_rich, simply say rich, and This is what all you need to do. But if you want to see the parameters which is inside this, just press Shift tab 2 times tab, and you will see the value of alpha by default 1, fit intercept equals to true, normalize equals to false, copy x, maximum iteration, tolerance level, solver, random state. All of these definitions are given below if you want to see related to the parameters over here. As you can see, copy x, maximum iteration, tolerance, solver, auto, svd, shellsk, lsqr, and so on and so forth. Their explanation as well about if you understand these terms and the statistics behind it. So for now, I will just go ahead with the default and initialize this. Once I initialize, I can fit it as part of the standard methodology, which is x comma y. Let me see. So 0 to 13 and then 13. Input contain NaN, so it contains the NaN, that means the missing value, as you can see it over here. So what do you need to do? Maybe an interview question. Well, what I'll do is I will create a line above here, Boston equals to Boston dot drop NA in place equals to true. That is it. I am removing all the NAs. Now there is no error. Alright, and if I see y underscore pred, I will say len reg dot predict based on what? Based on x, right? And now let's calculate the error. SQRT, mean squared error. First the y value, the actual y value, and then the predicted value, and then whatever your error rate which is coming over here. So this error rate, you can compare it with the linear regression technique, that whether this is better than the linear regression or the worse than the linear regression. If it is better, use it. If it is not better, don't use it, because it may happen that in cases where data is really perfect, your linear regression will give much better output as compared to this. Also, it is resource computed, and as you can see, there are like a lot of parameters that you need to adjust. In some cases it may be more expensive than that, but in many other cases where there is a high variance and there is an unseen data which can be anywhere on the data point or on the graph, then using this will be more useful. But what I wanted to show you a simple implementation, so that if you need to implement, all the steps along with the basic theory that you can use to understand the rich regression. So this is a quick implementation of rich regression. It has a lot to it. I mean, you can basically play around with the parameters, like say the alpha value from 1, alpha value equals to 0. If there is an interview question like this, what happens when you put the alpha value equals to 0? So when you put the alpha value equals to 0, just think it, what will happen? Well, it will be similar to your linear regression. If you don't trust me, you go ahead and execute this with alpha equals to 0 and then run the linear regression. The steps will be simple. You just need to import, like I have done it here, simply learn dot linear underscore model, import linear regression, and simply initialize it like linreg equals to linear regression. Same step for linear regression, then predict it, and then get the output. So your output of linear regression will be same as ridge regression when alpha equals to 0, and that is your one of the interview question that you can face. Also, if you want to go really deeper and really want to understand a lot of different parts, solver is one of the amazing feature which you may want to understand for the rich regression, because using which type of by default it is auto, it will going to pick it up, but it may happen that somebody may ask what will happen when you use the SVD or there are like a couple of other solver methodologies like the SAG or SACA, what really happens in that case and in which scenarios you may need to use it. If company is really into the field where they do the linear regression or the regression techniques for the forecasting or for the tuning of parameters, and this way you will be able to get a good grasp. But this is just for to start with the rich regression. So I hope you have found it useful. If you have any questions, there is a comment section. You can always comment and let me know about this, and you can find the data set in the description section, and then you can use it from there and practice it. Well, that's pretty much it, and I will then meet you in the new video.